to our next presentation. And here we have Marvin and Christopher, and they will talk about interaction combinators, the hidden patterns of computation. So, let us welcome the two of them and let us hear what they can tell us about it.
So, hello and welcome to our presentation, and the nice dancing triangles you just saw actually are already interaction combinators, and they form a model of computation. But first, before we talk about computation, we should actually ask the question, what even is computation? So let's start out with a very simple computation, 2 plus 4. Does anyone here know the result to that? Well, I don't know, so let's make this problem easier. Instead of writing 2 plus 4, we write 2 plus 1 plus 1 plus 1, and then just increment the 2 all over again. But now we have numbers, and I don't know what numbers are. So let's define them. So 0 is 0, 1 is the successor of 0, or 0 plus 1. 2 is 0 plus 1 plus 1, or the successor of 0. And because I don't always want to say successor, we introduce this notation where 0 is set, and 1 is s of set, 2 is s of set, and so on. And now that we know what numbers are, we can define addition. So we have two cases. If we have any number k and add the number with 0, we receive k. If we have k and the successor of n, we can duplicate the s, put it around the add, and then just add k and n. If this was a little bit confusing, don't worry, we got an example that isn't any more confusing. But if you do the computation and duplicate the s all over again, you end up with the result. And if you actually count the s's, you receive 6 times the s. So I think 2 plus 4 is 6. I hope so. Yeah.
Yes, so of course this is only a real minimal example. If you want to do actual computation, you will want to translate code to like these symbols and these rules that we have just seen. Right, so for example, now we have a function in JavaScript called add, which receives an argument x and an argument y and returns the sum of x and y. And you can then log the result of this function application. And then maybe some of you already know, you can actually abstract away from this, and you can define a constant that receives both arguments as an anonymous function, which this arrow syntax indicates. And then if you call the addition function with 2 and 4, it will actually substitute the 2 into the x and the 4 into the y, and then you can add the numbers. You will see exactly how this works later, but this is the anonymous function notation. And you can do this one step further and also abstract away over both of these values. For example, now we only receive one argument first, the x, and then after this we receive the additional argument y, and then we return the sum of x and y. And then if you want to call the function add, we actually have to call the function add once with the 2, and the result of this function application is another function from y to 2 plus y. And then if you also call this function with a 4, then you will actually, okay, this doesn't work. Then we will actually receive the sum of 2 plus 4, which is 6, right? And now we can go further.
Yeah, so I'm not really that JavaScript guy, so let's do a more mathematical notation. We can write x, right arrow y, and x, and if we apply the 42, we just take the x from the left-hand side, remove it, and then we replace all occurrences of x with the 42. So we get a function that goes from y to 42, because we replace the x. To formalize that, we can write it this way, and that's actually called a beta reduction. So on the right-hand side, you can see the m with the square brackets and x going to the n. So what this says, substitute all occurrences of x with the n. And on the left-hand side, you can see the function where we apply the n to the argument x. So we substitute all occurrences of x inside of m with the n. Yeah.
Yes, so, and this simple rule does actually many things at the same time. So it may not look very special, but it actually is really special. For example, of course, we have just seen it. it substitutes a variable. If you apply the n to a function from x to m, the value is substituted. For example, in a function that only substitutes the x and then returns a function from y to the substitution of x, for example, here applied to 42, then the x is substituted with 42. This is similar like in JavaScript or Python. When you call an anonymous function, then the variable is substituted. But also, it does something called erasure. So for example, if you have this function, but you don't bind the x, so you have a function from x to y and the return is a y, then applying this function to 42 will not substitute anything because x is not bound in the function, right? So basically, what we have is that the 42 is erased or destroyed. And then we only have a function from y to y because the x doesn't occur in the body of the function. So, for example, now if you have a memory or a low-level language, this will actually mean that the 42 will have to be physically freed from your memory because this 42 is now erased. And the beta reduction does this implicitly because it never says anything about memory management or anything. It just says substitute the value, but if it doesn't occur, you don't substitute it, but then it actually is erased. And similarly, you can duplicate the value. For example, if you have a function which we've already seen, like an addition function, then we substitute 42 into x, but now x is bound 2 times in the body of the function. Then 42 is actually duplicated and substituted 2 times and into the addition function. So we have addition 42 plus 42. And this also, in a memory management aspect, means that we actually have to duplicate the value physically. So the 42 will somehow need to be duplicated on your memory so you can actually use it twice. And of course, this argument could also be an application, a function, or anything else. So our reduction system basically has to be capable of duplicating and erasing arbitrary data which we have in the system, for example, functions or applications. And also, which we've seen, that application, if we actually have a large function application, for example, factorial of 42, which is a large number, if we want to substitute this into the addition function, it's not clear whether this value has to be duplicated immediately. For example, the function is not evaluated and explicitly substituted into add factorial of 42 plus the factorial of 42, or if it's first evaluated to a large number and then substituted and copied, so that only the result of the factorial is actually duplicated or cloned. So this is not obvious, so it's also implicit in this rule. And then we also have the order, which is a bit confusing, and it's not really like some common notion of explaining this. But if you have this function application and you have on the left side a function, for example, x to m, and the argument is n, only then, if the left argument or the left side of the function application is actually a function, then the n can be substituted into x. And if the left side of an application is not yet a function, like here, then actually the value is not substituted. So we actually have to wait until the left side of the application becomes a function, and then only can the n be substituted into the x. So it's a bit confusing, but we will see why this is relevant later.
So what we have been hiding from you all the time is that when we have anonymous functions plus function calls, this is actually already Turing complete. So if you don't know what Turing complete means, it's basically a very informal definition. Every program you can write in your favorite programming language is Turing complete. But now you might want to ask, well, what about numbers? We don't have numbers with anonymous function and function calls. I argue we actually do, because we can write 3, as we already saw previously, as the successor of some number. So we just have a function that takes another function s and a set, and then just applies s 3 times to the set. So that would be 3. And with this, we can also increment the number. And we do this by taking an n and an s and then set, and then we duplicate the s around the original value, and then apply the s and the set again to n. So now we have numbers, but in most programming languages you also have loops and recursion. So how do we solve this?
Yeah, so this is actually really confusing because only with the beta reduction rule that we have just seen, like the function application, it's not clear how to do something like this, where you have the factorial and it receives an n, and if the n is smaller than 2, then we return 1, and else we multiply the current number n with the factorial of the previous number, so with the factorial of n minus 1. And doing this is not possible in the pure lambda calculus immediately, or with pure anonymous functions and function calls, because this factorial is not actually in scope, this recursive use of the factorial, because we only basically have the right side, the right side of this definition, like the n to n smaller than 2, etc. This is actually the definition and our term that we are evaluating. The left side, the construct, does not actually exist. So the factorial of the previous number can also not exist this way. So what we instead do is we define another function, underscore factorial, which receives a factorial as a first argument. This is actually the factorial function that we want to use. And then in the recursive call to the factorial of the previous number, we now also apply the factorial function, because the factorial function now receives as its first argument the factorial function itself. So this is a bit confusing, but now if you want to define the actual factorial function, we have to take this underscore factorial function and apply it to itself. And this is correct code, so you can actually write this in using only anonymous functions without these definitions on the left side. And this is possible because we never actually access anything outside of the scope of the right side of the definition, right? So we can also see this in, basically we have this, okay, this is another thing. So what we actually are talking about, maybe this is not clear, or maybe this is clear to some people here. What we're actually talking about is the lambda calculus. So in our system, we do not actually have these numbers like 2's or the multiplication function, but we have argued with a few examples now that all of these functions, all of these operators like addition or numbers or multiplication, etc., are all possible to be encoded in the lambda calculus itself, like without anything additional, only with functions and function calls. Yes.
So now that we have introduced the lambda calculus kind of and beta reduction, what about the reduction order? So if we take a look at the nice factorial function again, you can see that we can just apply the factorial to itself over and over again, or we can apply the 42 or the 41. So if we would just apply the factorial over and over again, we could do that for an infinite amount of time, for an infinite amount of reductions. But if we decide at some point that we want to apply the numbers, we actually end up with the result. So that's the factorial of 42, and that's the result. I think you all knew that, because of 4 plus 2. So reduction order does actually matter. Yeah.
So yes, so in a way, reduction order does matter, but in another way, it does not, because the reduction order can modify like the interaction or the reduction count. For example, we have seen if we iterate in the factorial function application and we just apply the factorial to the factorial itself infinitely times, we can end up in like an infinite recursion and we will never actually get the result. But if we will later then focus on the surrounding terms and reduce them, then we will always get to the same result. So this is a fundamental law of the lambda calculus or this computational model, that we will always end up in the same result, even if we take different routes of getting there. So we can basically reduce the application or the functions in the applications arbitrarily, and you will always get to the same result. And the important part is that in this graph, so we have a term m, and it's eventually it will reduce to the term m prime, and the steps are, for example, if you take one route and you reduce the left side or the n smaller than 2 on the left side, and on the other side, m2, you reduce the factorial of factorial 2, this application, then no matter how many applications you eventually do, you will always get to the m prime. So, but the left path could be longer than the short path, than the right path, or the right path could be longer than the left path, etc. And the shortest path is actually called the optimal path. You will see why this is relevant later, but it is possible to evaluate this factorial function by only taking the shortest path, and then you will have the least amount of computation, because you actually did the least amount of work to get to the result.
So we call this so we call this property that we always end up with the result Whaa confluence, just to add to that real quick.
Yeah.
And now to recap.
Yeah, so what we have just seen, so this was basically an introduction to what we want to introduce now, because what we have seen is that we have, in our system, we have functions and applications, and we have very minimal rules. We basically only have this function application rule and a substitution rule, and this is what we want in a computational model. So we actually want to find the most elegant computational model, and we argue that we have basically a contestant which we think is really good. So in this case, our system that we want to introduce next also has minimal rules, and we want to have no implicit behavior. For example, in beta reduction, we have seen that we have implicit duplication. On erasure, it's not entirely clear when things are duplicated or erased. It's also not clear when things are shared and when things are substituted immediately. And then you will sometimes do, for example, the factorial 42 2 times instead of calculating it first and then substituting it. And we also only have the Whaa confluence, which means that one path could be longer than the other path, or the reduction path. So we actually want a one-step confluence. It's called the strong confluence. And then we can actually reduce in parallel, because it doesn't matter in which order we reduce the terms, because all reduction paths will be the same length. So it doesn't matter how we distribute the terms or the variation of the program, because all paths are exactly the same.
We try to solve this with the interaction nets, which aim to solve all the previous problems we have mentioned. And the very basic building block of an interaction net is a so-called agent. You can already see it here. And it's made of a principal port, which is the one at the top. And then it has multiple auxiliary ports. It actually can have any number of auxiliary ports. It could be 4, it could be 5 or 0. And there are also different types of agents. So we want to differentiate them in this talk by shape or color. And now if you have those agents, you can connect them to each other. So you can connect principal ports to principal ports, auxiliary ports to auxiliary ports, or principal port to auxiliary ports. So it does not matter. And whenever you build such a net, you can abstract away from it like a black box. You just take the ports which aren't connected, extend them outwards, and you end up with a package which just encodes the net and leaves the unconnected ports. So how do you compute things with them? Whenever two agents are connected with the principal port, they interact with each other. And when they do, they produce a new package. It's important to notice here that they both have two auxiliary ports. The resulting package also has those auxiliary ports. So they just produce something new, but the auxiliary ports stay.
Yes, and it's not clear what is inside this package. It could be an arbitrary net where these wires are free, so they reach out of the net.
So that was a bit abstract. So let's actually introduce interaction combinators. Those are 3 types of agent which are actually already Turing complete. The first one being the duplicator, the second one being the constructor, and the third one the eraser. And they can interact basically in 2 ways. The first type of interaction is annihilation. Annihilation happens whenever 2 nodes or 2 agents of the same type interact with each other. So in this case, we want to look at the interaction of nodes with 2 auxiliary ports. And you can see when they interact with each other, they just cancel each other out, but they also connect the wires. So Y2 gets connected to X2, and Y1 gets connected to X1. And those are exactly the auxiliary ports of the 2 nodes. We can also define annihilation for agents with 0 auxiliary ports, also the eraser. And whenever 2 erasers interact with each other, they just cancel each other out and produce nothing. The second type of interaction is commutation. So commutation happens whenever 2 agents of different types interact with each other. And this interaction actually is really cool. So at the bottom we have a duplicator, and at the top we have the constructor. And when they interact with each other, they duplicate themselves. And so the duplicator gets duplicated at the top, and the constructor gets duplicated at the bottom. And if you look closely, you also have two auxiliary ports at both nodes. And we end up with two principal ports from the duplicator, which then get connected to the auxiliary ports of the constructor. And the same, of course, goes for the auxiliary ports of the duplicator. And then also the auxiliary ports of both nodes get wired together. The second type of commutation is whenever a node with two auxiliary ports interacts with an eraser, the eraser just gets duplicated. And Lafont, that's actually the one who introduced interaction nets, argued that the fundamental laws of computation are commutation and annihilation that we just saw here. So one cool property of those agents is also if we have a package connected to a duplicator, the package gets duplicated.
Yes, so in our case for the lambda calculus, which we will see later.
And if we have an eraser connected to a package, the package gets erased. That isn't actually directly obvious from what you just saw now.
So importantly, if you duplicate this this package could contain any net, right? It could be any agents connected to each other. If the duplicator interacts with the agent within the black box, within the package, then it will iteratively duplicate the net, because at each step that the agents or a single agent will be duplicated, and the duplicator will continue at the auxiliary ports of the agent that it has duplicated. So eventually it will duplicate the entire net that is inside the package. And same with the eraser, it will iteratively erase the net until it is completely erased. Yes.
So let's look at another property of this net called locality. So we have just an arbitrary net here, and we can see that there are two nodes or agents which want to interact with each other. And if they interact, they annihilate themselves, as you saw earlier, but it's also important to notice here that the rest of the net does not change. So they just produce a new package inside the purple box as we draw, but the rest of the net remains unchanged. And this leads us to the next property.
Yes, so the one-step confluence, which we have previously argued, which is the goal of our computational model, we want it to be confluent with a one-step relation, which means effectively, if we have this this graph where an M could either reduce to an M1 or an M2 with different interactions applied. For example, if you have a huge net and there are different kinds of interactions that you could do, on the left side you would do one interaction, and on the other side, M2, you do another interaction. Then if you do continue and do similarly like interactions that are possible in the graph, or in a net, then you will eventually get to the result. But importantly, because of the locality, the n is always equal to m. So it does not matter in which order you reduce or interact the agents, because you will always require the same amount of steps until you reach a common term m, or a common net m. And this is really important because then you can actually parallelize the interaction reduction. And then you can, for example, assign each core of your processor a single interaction, and then they can do these interactions at the same time. And then you can do the next interactions that are the results of these interactions. And it does not matter how you assign these interactions to the individual cores of your computer, because this rule exists, and it does not matter how you actually reduce the interactions, because they always require the same number. This is a bit confusing, because this actually means there is not a shortest path in the reduction that you could take, because there are no possible infinite paths or paths that are longer, and it means that essentially it always is the optimal path. So basically what we do in the reduction, if you reduce an entire network, you will always require the least amount of reductions or interactions, because there is no way to do more reductions or less reductions. So we will see why this is later if we translate the lambda calculus to this network. Yes.
So we already talked about translating the lambda calculus to these networks. And one trick we need to introduce before is called polarization. So as you can see, we labeled the ports with plus and minus. And it's just like with magnets, you can't connect two poles or ports of the same type, so this connection is invalid. But if we change 1 plus to a minus here, they can be connected together. So this notation is a bit confusing, so we use arrows instead. And if the arrows point into the same direction, we can connect the nodes. And if they point into opposite directions, we can't. And this notation also has a nice implication, because whenever arrow points outwards of the node, in an abstract sense, you can imagine that the port produces something, and when it points inwards, the port consumes something. So you can kind of imagine the flow of the network with this.
Yes, what this means exactly we will see now, because it's not very clear what these arrows actually mean. But for example, if we now polarize the interaction combinators that we have introduced, you can get the lambda term. So it looks a bit confusing, right? But so let's say you have this function x to m. This is interesting. No, what happened? I have no idea. Where are we? Oh, what happened?
Gerade was richtig gesagt. I mean, it's also nice.
Yes. Intense.
So maybe we could just. How much time do we got left?
I don't know, it's okay.
Okay. So
maybe it just crashed.
no, we actually have a demonstration because it's all abstract, but something crashed. So just give us a second, and we'll be back. But I also like the dancing triangles.
Yes. Yes. So sorry about that, but now we're back. So basically, what we have seen is that we can polarize our action or our agents with polarities. So now that we have this function on the left side, which is the function that we have defined earlier, an anonymous function, it receives an argument x and returns a term m. Then we can actually write this as an abstraction agent. So this is like the constructor agent, but now we have put a lambda in it, because on the left side, we will now always put the translation of the x. So this is actually just a wire that connects into the m. So if whenever x is used in m, there's a wire from the x to the m. So it looks a bit abstract. We will see this again later. But the abstraction also produces something, which is to return the result after the abstraction has interacted with the application. So now, for example, the application on the bottom left is encoded as an agent, which on the top interacts with a term m. Again, this m is actually a translation to an interaction net. And on the left side, there's the n. And this n is consumed as well as the m, because an application, if you think about it, actually just returns or produces the result after n is applied to m. Which we see on the left side, if we apply n to m, the result of this will actually be the application or the substitution of n into m if m has converged to an abstraction, which we have previously talked about with the order. Right, and then we also have the duplication in the erasure nodes, but now we have polarized them into opposite directions. For example, if we want to duplicate an abstraction agent, which is the top left, we will actually have to use the top duplicator, which is the black node, because only the black node with the inward-facing principal port interacts with the abstraction, and only the bottom duplicator interacts with the application at the bottom left, because the arrows are facing this way. We will see this in an example later. So now, for example, if we want to now encode the beta reduction rule, which we have previously talked about, which is the function application for functional programming languages or JavaScript or anything else. If you now have the abstraction node at the bottom and the application node at the top, you will see that they fit together and they interact by having the n as an argument at the bottom at the top right, and the m, which is the body of the abstraction, at the bottom right, and then the x of the abstraction will actually, or should actually be connected to the n, because the n should be substituted into the x's that exist in the term m. Right? So it's a bit confusing, but if we look at it, right, this is actually the interaction rule that we have previously defined, and they are still true even if we have polarized the agents. We still have this simple interaction rule that says we now connect m to the return of the application, and n is connected to the x, which may occur in the m. Right, so specifically, we also now see the flow, basically, of this interaction. That's why we introduced the arrows, because the m is returned, and the n is substituted into the x that may occur in m. So I think this is actually a really intuitive visualization if you understand that it specifically does this, like it substitutes n into x, which may occur in m, and the result m is returned by the application. And that's exactly why these two agents have these polarizations, and that's why they have the ports labeled like that, because then we can represent this substitution exactly like that. Right, and here's an example, which is a term. On the left side, we have a function which receives an f and applies f to itself. This could be an arbitrary function, but now we actually apply a function that receives an x and returns an x. This is called the identity function. And we substitute this function into the f on the left side. So now basically what we will expect to be the result is the application of the identity function to the identity function, which is of course the identity function, if you can imagine that, because you will now look at an example if it works. Here. Okay, so right, this is actually a simulator, which is the exact translation of this, right? So here on the bottom right is the application, or not an application, it's a, so this is the L, this is a lambda, an abstraction or a function, which receives an x here, and the x, or the f, as we have named it here. So this is the left side of the term. F is duplicated by the application from f to f, which is here is the f, and it's duplicated as it's put into the duplicator, and then f is put into this application agent, and then f is applied to itself. And this right here is the right side, which is exactly the x to x, because this binds the x right to its return, or the term itself. So if you have, this is the variable of the agent, it basically gets connected here, and then it goes right back into the return of the lambda abstraction, because so the x to x returns exactly what it receives, right? It receives an x and returns an x. So we can then quickly reduce this. So for example, we have now marked the agents that can interact in red. So we have this abstraction and this application, and then they can both interact with each other, which this, so I think it went a bit quick, but what we have basically seen is that this identity function, which is the right side here, right, it's the x to x, is now substituted into the f. So what we now have is that the f, or the identity function, gets first duplicated, because we use it 2 times in the function. And then we have this 2 times here. And then this is an intermediate reduction that we have to do to actually do the duplication completely. And then we have 2 identity functions, which is exactly the identity function here, which is duplicated and then applied to each other. And then we apply them to each other using this application agent. And if we do this, we will get back the identity function, which is the result of the application. And don't mind the I and the T, they are not important.
So what's also important to note here is that you could reconstruct a lambda term back from that. So you translated the term into a net, reduced the net, and got back a term. So that's also important to mention.
Yes. So now a short recap, what we have actually done. So we have we have a minimal system, right? We have only 3 agents, which we have previously also had in the lambda calculus. We had minimal rules. So, but this system is also Turing complete. So you can actually do anything a computer can using only these 3 agents, right? And you also have a very elegant and explicit memory management, because duplication and erasing agents will always happen explicitly with the duplication or erasing agent. And we can actually reduce this in massively parallel way, because we can just reduce them arbitrarily on many CPUs as we want, because it does not matter in which order we reduce the agents or the interacting agents, because we will always get the same result. And also, we can encode the lambda calculus in it, as we've seen, and we can even read back a lambda term after the interaction net has reduced, which we have not explained right now, but we can actually extract the lambda term after we have reduced the interaction net. So basically, if we translate a programming language, a functional programming language, to interaction nets, you can reduce it as an interaction net and then get back the result after it has been reduced completely.
So that sounds nice, but is there a catch?
Yes, so actually, there is a catch that that we've been hiding. It's a bit confusing to explain, and we will probably not explain it completely, but we have previously said that if two equivalent agents interact, which we call annihilation, then they will always just cross over, right? Which is similar to the beta reduction, where we connect x1 to y1 and x2 to y2. But this is not always the case. If we want to duplicate a term that duplicates its arguments, it may contain conflicting interactions. This is basically, we will then have to do this duplication interaction which duplicates the duplicator, because if you want to duplicate a term that duplicates its arguments, you will also have to duplicate the duplicator and not just throw away the duplicator as we've done previously. But if we duplicate a duplicator in the same term, basically in some people call it the radix family, then you actually have to annihilate the duplicators. It's a bit confusing, and it's just important to be aware that there are actually limitations, otherwise everyone would use these, right? Because they're actually really efficient otherwise. But this looks a bit confusing, but if you have the abstract algorithm, which is the algorithm or the algorithm that we have introduced without anything else, which is exactly the same as we have introduced it, then terms cannot duplicate terms that duplicate its arguments. And this is a limitation that can occur in actual programs. For example, if you define numbers as we did with duplicating s, then you cannot duplicate this number and apply it, for example, to a function that binds this number 2 times, because then this function or this number would have to be duplicated, although it duplicates its arguments. And if you add labels, so these are 2 steps that are possible to fix this problem. If you add labels to the duplicators to say, okay, in this case, if 2 duplicators have the same label, then we actually want to annihilate them. And otherwise, if they have different labels, then we want to duplicate the duplicator. Then you can do one thing more. It's this confusing sentence. If terms that duplicate the arguments are duplicated, the duplicates cannot duplicate each other, which is much more rare. So this will actually not happen in most cases. So that's why this system with labels is already really good for actually computing your programs in parallel and in a massive way, because then you can just use these interaction rules and just have to be careful of the labels, but otherwise it's fine. And if you want to support all functions, so you do not have this limitation, then you can actually introduce something called bookkeeping or an oracle, which has a cool name, because then you do not have limitations. You support the full lambda calculus, all functions that are possible, but you will have an overhead because you will have something called delimiter nodes or croissants. It's confusing, so we will not introduce it here, but it is possible to support all functions, but it is not necessary to have this overhead. Right. So another thing that you may hear if you hear people talking about interaction nets is optimality. So we have previously seen that we can actually find the optimal path in a reduction of a program, which is the shortest path in evaluating a program. And we have also seen that in interaction nets, basically all reduction paths are optimal because there is only one path that you could take from the length side, right? all paths have the same length, so all paths are basically optimal. And if you encode the lambda calculus in interaction nets, you can basically argue that you can also reduce the lambda calculus in an optimal way this way, because the interaction net will always require the least amount of reduction steps or interaction steps to reach the result of the lambda term. And this, of course, if you want to support the full lambda calculus, I've just told you, you will have an overhead of the oracle, but if you do not want to support all lambda calculus functions, you will still have this optimality property, even without supporting all terms. And then there's also a problem with detached nets. It again sounds a bit abstract, but if you have a factorial of 42 and apply it to a function that does not bind the factorial of 42, then we will basically have to erase this argument. And we have seen that if you erase a package, you will iteratively erase this package. And by erasing it iteratively, you will, as a side effect, also evaluate the package. And for example, if you have the factorial and you do not use it, as we have shown you, this factorial will still be evaluated, which is not what you want if you do not use the argument. So therefore, we can do something called detached net things, algorithms, to find out whether a network, like for example an eraser interacting with a package, is not attached to the main network anymore. And then we can just garbage collect it completely without evaluating it, without erasing it iteratively, and then we also bypass this iterative erasing of the net. And then we can also use parallelism if you somehow combine it with the detached nets. And this is still an open problem. So if you want to work on this, there's actually a lot to research about this. Right. Yeah, so this is not that important, so we're actually almost out of time. So you can also extend the interaction nets. We have only used 3 agents, right? But you can also add more agents, for example, to support I/O, if that's something your language should support, or you can support built-in operators to add functions or to add numbers using the addition function of your processor itself, like the instruction. And you even can have ambiguity, so the net does not always do the same. And this is maybe interesting to the statisticians. I don't know. You can, for example, do a parallel OR where you evaluate both sides at the same time, and the one that evaluates faster will be the return network. And this is also interesting. So all of these extensions do exist, and all of these can be arbitrarily added. And the rules that we have stated, like confluence and parallelism, still exist even if you extend the network with agents, except with the ambiguity, because then confluence will be broken. Yes, so use cases. So that's maybe why you are here. So you can use these interaction nets to parallelize your programs to, for example, if somehow in the future there was an implementation of this, an efficient implementation, then you could just parallelize your program on all cores of a data center without thinking about mutexes or semaphores. You can just parallelize it immediately without doing anything else, because all of these interactions, all of these agents can then just be distributed across all cores of your processor. Right, and then also optimal reduction is sometimes interesting if you want to find the shortest path in your lambda term, right? It's something that is neat because it requires less computational power, because then you will have actually the shortest path. And also, hopefully, maybe we have shown you a nice way to think about computation in a way that computation by itself is really just duplication and erasing of terms. And this is actually the most important part of computation itself, like the annihilation and commutation, which just encapsulates the duplication or the iterative duplication and the iterative erasing of terms. And this is all that computation actually does. So this is a pure way to think about it.
So we also brought some resources. We get that this is probably a bit confusing. It's always hard to think about new models of computation. So if you already heard about the lambda calculus and came from imperative programming language, this was probably already hard. So if you say this was interesting, but I want to learn more about it, you can check out these resources. I think the top link is probably the most important one. Or you can just ask questions now, or if you have any questions later, there's also a deck number, and we will publish the slides.
Yes. Thanks. That's all.
Well, thanks for the great talk, the two of you. And I would like to ask if any one of you has some questions. Over there.
Nope. There we go. Yeah, thanks for the talk. It was super interesting. So I was wondering, so you talk about, of course, how this sort of makes explicit when sharing or copying and deletion of values is happening. And I know that, of course, lambda calculus is closely related to type theory. And in type theory, you have linear type theory, which also kind of does the same move. So is there a sort of relation between linear type theory and these interaction nets?
Yes, there's a close relation. And in fact, you can encode linear logic in interaction nets. And I think actually most of the research, or the initial research about interaction combinators went into the area of like linear logic and how to make this application like explicit even in the case if you do not always want to have the capabilities of just duplicating terms or something. But yes, there's a very close relation. And I think that's actually why it's interesting. Linear logic by itself is interesting. And yes, there's also a programming language called Whaa, which is fairly new. They recently switched to using interaction combinators, and it's a programming language with linear types. And I think, I'm not sure exactly what they're doing, but this is really cool. So yes. This is very closely related.
Thank you.
So you said that there are currently no efficient implementations of this. So what about the inefficient implementations? Like, what do they do? Or can I imagine like it take a C program and it translates it, or how do they work?
Yes, so I'm not sure I said that there is no efficient implementation because there are some implementations. For example, HVM, which some of you may have heard, it's a higher order virtual machine. And this implements the abstract algorithm with labels that we have seen. And this actually is really efficient. They can do several hundred million interactions per second, and they can be distributed across all your cores. And they have actually a programming language called Bend, which is a mix of Python and Haskell. And if you write, for example, a quicksort in this language, then you can run it on a single core, and then it's acceptably fast. I mean, it's still a bit slower than comparable implementations. But then if you distribute it across all cores, or for example on a GPU, then it is actually a lot faster by magic. So there are actually efficient implementations. But HVM, for example, does not support the Oracle or the bookkeeping, and it will not support all lambda terms. So if you want this, this is a limitation, but there also exist implementations about that. For example, OptiScope, which is fairly new, which supports the entire lambda calculus, and it's also fairly efficient. Yes, but it's not parallel.
Is it always more efficient to use the shortest path representation memory-wise?
So in general, so these interactions can be imagined as being O of 1. So basically it does not matter, but effectively you will want to prioritize annihilations before commutations, because commutations can create new agents and annihilations do not create new agents, as we have defined them at least. And then it will be better to prefer doing the annihilations, because then the maximum memory will be lower than if you would do all the commutations at the first they are introduced. So there is the reduction order can matter, but it does not effectively matter if you, yeah.
Is there research in the other direction? For example, if you have a program that is memory-wise too large for your current processing unit, then it may make sense to lengthen the path, but thereby thinning the memory, right?
I don't know about that. I don't know. Sorry.
Okay.
Interesting.
these diagrams and their relations that you've shown look a lot like what's in math called a bialgebra and their relations. Are you aware of that similarity? And if yes, do you know whether there's like anything like about studying these interaction nets using algebraic theories such as that?
So there's a lot of mathematical background in these rules. We are both not mathematicians, and I cannot speak about that, but there is a lot of algebraic arguing about these interaction nets. So for example, the geometry of interaction machine has a lot of these mathematical notations about that.
So do we have any more questions? Well, I'm too... Oh, there it is.
Thank you. So this is for untyped lambda calculus, essentially. And how would you go about adding types to this?
Yeah, so basically we have already added types. It was a bit implicit, which is the polarities. They are, in fact, like a kind of type. But if you also add named types, there are papers about adding types. But I do not really see the reason in adding types, to be honest, because it's basically the back end of a programming language. And so I know this is a bit, so this could be discussed, but in this case, it does not really add any benefit to add the types to the back end of this language. But I mean, you can add it. There is research on that. For example, the simply typed lambda calculus, you can also encode this. Yeah, I don't see much sense, but you can of course do it.
But you could also imagine a programming language which has types, and then you can just type check your language and then translate it into interaction nets. That would be possible.
Except with dependent types.
So do we have another question? Well, if not, I'm sad we didn't see the dancing combinators anymore, but apart from that, let's thank our two speakers for this great presentation.